So we've been saying that the output of a linear time-invariant system is the input convolved with the impulse response. Therefore, the impulse response itself tells us everything we need to know about the LTI system. If I can get the output for any input, then all I need is the impulse response. So, therefore, the impulse response itself must provide some information regarding the other properties of the system, like memoryless and causality and invertibility and stability. Okay, so in this video we're going to look at memoryless and causality in LTI systems. What does the impulse response have to look like for these properties to hold? All right, so let's start with memoryless. And if you recall, memoryless means that the output can only depend, so the output at time n, for discrete time, can only depend on the input at that same time. Okay, we can have constants out in front, we can square it if we want, we can add constants, we can add the linear term, whatever, but it can only depend on x of n. It can't depend on future values of x, and it cannot depend on past values of x. Okay, now let's run with that idea. And if this is an LTI system, so given that it is linear and time invariant, if I put x in and I'm going to get y out, we know that y is the convolution of x with h. Okay, and we know the mathematical definition now of convolution, and we know that convolution commutes. So I can write this as k goes from minus infinity to infinity of h of k times x of n minus k. All right, so that's the output. And let me expand this output, or let me expand the sum rather. So I've got an infinite sum, so it starts at minus infinity and it goes to minus infinity. Then maybe I'll start writing the minus 2 term. So then I've got h of minus 2 times x of n plus 2. And then there's the k equals minus 1 term, so that's h of minus 1, x of n plus 1. Then the k equals 0 term, plus h of 0, x of n, right? And then the k equals 1 term, h of 1, times x of n minus 1, and then and then it goes to infinity, right? We just keep going like that. So this is the output. Now remember what we said about memoryless was that the output y at time n can only depend on the input x at that same time. Well, there it is, right? There's the input at the same time n, but here's the input at a previous n. Here's an input at a future n, 2 samples in the future, 3 samples in the future, and so on. So if this thing is going to be memoryless, what can you say about h of negative 1? What can you say about h of negative 2? H of 1? All of these things have to be 0. They all have to be 0 so that it wipes out the contribution of x in the future, right? 2 units in the future, 1 unit in the future. H of 1 has to be 0 so that it wipes out the contribution of x in 1 unit in the past, 2 units in the past. So that leads to the conclusion that a memoryless LTI system must have an impulse response, h, that is 0 for n not equal to 0, right? H of 1 must be 0, h of minus 1 must be 0, h of 2 must be 0, h of minus 2 is 0. This one is okay. H of 0 can be non-zero, so that the contribution of x at the current time, is allowed. That's fine. So this is the condition to be memoryless. All right, so what does that mean? Well, remember, that means that if I put in an impulse into the system, right, I get out something. Well, what I'm telling you is that if the system is memoryless, then I have to get out something that is 0 for all n not equal to 0. That is, I get out a scaled impulse. Maybe we'll say it's scaled by k, some value k. But it has to be 0 everywhere but the origin. So if this is the input, right, this is the impulse, this is the impulse response. This is the impulse response. It has to have this form for any k. So what kind of input-output relationship is that? Well, xn convolved with hn gives me the output. And now we're saying if the system is memoryless, then h has the form of some constant times an impulse, right? That is, that the impulse response has to be 0 everywhere but the origin. So I can bring the constant out, and then I have x convolved with an impulse. But what is the convolution of a signal with an impulse? It's that same signal. So this gives me k times x on the left, and that is equal to the input, or the output. So this is my input-output relationship. If the system is to be memoryless and linear time invariant, I would have something like this. And this is also true in continuous time, that y of t is some constant times x of t. So these are proportional blocks, right, or amplifiers. Proportional blocks are memoryless and linear time invariant. Over here, the constraint, similarly for continuous time, is that h of t equals 0 for t not equal to 0. Okay? So now, related to memoryless is causality. So remember what it means for a system to be causal. Here, the output at the current time n cannot depend on future values of the input. So it cannot depend on x of n plus 1, for example. It cannot depend on x of n plus 2 or x of n plus 3. It can depend on x of n, the current time stamp, and the previous time samples, right? n minus 1, n minus 2, and so on. So what that means for causality now is that this has to be 0, so that it wipes out the contribution of x in the future. This has to be 0 to wipe out the contribution of x in the future. And all of these must be 0 to negative infinity. However, h of 0 can be non-zero, so that the current x is contributing to the output. This h1 can be non-zero, so that the previous x can contribute to the current output, and so on. So we conclude, for a causal LTI system, the impulse response must satisfy, it must be equal to 0 when n is less than or equal to minus 1. Or said another way, when n is less than 0, right? So that's the condition for discrete time, for an LTI system to be causal. And for continuous time, it's similar. H of t must be 0 for t less than 0. Okay, so let's kind of just sketch that out. That means, remember, h is literally the response to an impulse. So here's my impulse. I put this in, right? 1. And what I get out? Well, the exact thing I get out depends on the system, depends on the circuit or whatever it is. But if it's going to be causal, it has to satisfy this. It has to be 0 when n is less than 0. So it has to be something like this. And then at 0, it can do whatever it wants to, depending on, the circuit or whatever. So this would be, for example, a causal LTI system, again, because it's 0 for n less than 0. But imagine, and we can make sense of this with the following thought experiment. Imagine that I put in an impulse and I were to get out something like this. Here's 0. Maybe I get out, here's -1. Okay, this is h. So again, this is the impulse. This is the impulse response. Now, notice that our impulse response here does not satisfy h of n equals 0 for n less than 0 because of this sample right here. Okay, so this would not be a causal system. And we can understand that in the following way. Here, I've got zeros. I'm inputting 0, 0, 0, 0, 0, 0, and then I put a non-zero there at time equals 0. But look what I get out. I get out something at -1, something that happened before I put in this non-zero value, right? I put in a non-zero value at the origin, but I got something non-zero right before that. So that must mean our system, whatever it is anticipating me putting in this sample. Somehow it knows that I'm putting in that sample before it happens. Well, by definition, that's not causal, right? And so we can further understand this constraint, and similarly this constraint for continuous time. Okay, so we've seen the conditions of memoryless and causal. Again, these are now LTI systems. If we have a linear time invariant system and we further impose memoryless and causality, what does that mean regarding the impulse response? Okay, so we see that here. Let's move on to the other properties that we've talked about before.